Hello, everybody. Thanks for coming this lovely afternoon. My name is Mack Hopen. I'm the Commercialization Manager at Modern Hydrogen. We are a technology developer working on distributed methane pyrolysis technology. So taking renewable natural gas and natural gas, turning it into gaseous hydrogen and solid carbon. So the premise of this talk is we should be making better use of the carbon that we're emitting today, and that's what we're working on. So as many of you here are aware, the needs for sustainable hydrogen production are poised to grow exponentially over the coming decades in order to meet net zero targets. Industries that currently use hydrogen need to clean their hydrogen up. Many industries that don't use hydrogen are planning to make use of it as they continue to grow and decarbonize. Things like transportation, aviation currently don't use much hydrogen and are poised to make up a significant portion of growing demand. About 90 million metric tons or so per year of hydrogen are produced. All of that, 95+%, today is done using steam methane reforming or from fossil gas itself. So there is that immense challenge in the short term to clean up that demand while also preparing to meet the growing demands there of something on the order of 80 million metric tons a year of new clean additional growth by 2030. If we are reliant solely on one or two technology stacks to get there, that seems to be a pretty risky endeavor to put all of our eggs in one or two technology baskets, and that's where methane pyrolysis comes in. At a simple level, methane pyrolysis is the process of converting CH4 methane molecules into solid carbon and gaseous hydrogen. There's a bunch of different ways you can do that. The simple version is you excite those molecules using heat, whether that be from a plasma torch or a microwave or just thermal energy itself. You can do it a couple other ways, with catalyst, without a catalyst, but the main takeaway is you're exciting those methane molecules to the point where they break apart, and as soon as that happens, the carbon comes out as a solid. If any of you want to see some solid carbon later, I've got a little jar of it up here. It looks like black powdered sugar. It dissociates from the gas stream, and you're able to then take it out of the reactor, continue operating, and put it to productive use. So there are a bunch of benefits of methane pyrolysis, starting with the energy requirements. Methane pyrolysis as a process requires about 1/8 the energy input of electrolyzers to produce the same amount of hydrogen. So if you look at a 1 megawatt rated electrolyzer, you get something around 400 kilograms of hydrogen per day. With that same amount of power in a methane pyrolysis system, you can make about 3,000 kilograms of hydrogen per day. That's huge, especially in electrically constrained environments. We talk places like California, the Northeast. Everywhere really today is electrically constrained as electrification continues. We should be making the most of those clean electrons and using the most efficient processes where we can. Another huge benefit is that it avoids CO2 production. The carbon that's in that gas stream, in natural gas or renewable natural gas, is not becoming CO2. You are avoiding reacting that carbon with oxygen, so you're able to produce a solid powder like this that you can make use of. With the right feedstocks, methane pyrolysis can actively remove carbon from the atmosphere. We're working on a project right now in the state of Washington that's taking dairy biogas, decarbonizing that, breaking it down into carbon and hydrogen, and that was a carbon neutral gas that has now had the carbon removed from it. So the hydrogen that we're producing that's going into a power plant is negative emissions hydrogen, and the asphalt that we're making is effectively sequestering carbon in the roadways that was at one point in the atmosphere. It's something we're really excited about, and it's an amazing value of pyrolysis that you're able to get below zero emissions in many cases. It's also much simpler to manage, both from a carbon management standpoint and from an energy delivery standpoint. Hydrogen's an amazing molecule. It's really hard to move around and store. So our philosophy is you should be doing that as little as possible. Make your hydrogen on site and then move the carbon in the solid form instead of as a CO2 molecule. We're still a long ways away from having CO2 pipelines and infrastructure and wells to the point that we can capture enough CO2 to offset turning these power plants and these industrial processes into carbon capture systems. With a solid powder, you don't face many of those obstacles. And really the main value that we sell and the systems that we're building is you can integrate what we're doing with existing infrastructure. We don't need to wait for hydrogen delivery pipelines. We don't need to rely on trucks moving effectively rocket fuel across the roads. You can integrate this with the existing natural gas infrastructure. Think about our systems like a filter at the end of the gas pipe for carbon. Again, I mentioned the emissions intensity in CO2. Pyrolysis is amazing because it can go negative, but The unspoken component of the emissions intensity of hydrogen is often that middle piece, the transportation. The US and Europe have rightly focused on production emissions, making sure that we minimize the emissions at the point of production. But if you've got to put that hydrogen on a diesel truck, excuse me, and drive it 600-700 miles to get it to its point of use, are we really much better off from just burning natural gas or using diesel in those applications to begin with? The math says probably not. The trade-off with a standard tube trailer truck is about 75 miles or so, where you break through the emission threshold set by 45E clean hydrogen production rules. So our philosophy is you should make your hydrogen where you use it on site. If you need to build out electrical infrastructure to do that, you should try to do it. But if that's a gate to you, there is still a way to make use of the natural gas infrastructure in a clean way. So that is getting me to what is our innovative approach. I mentioned that there are a bunch of different ways that you can excite those methane molecules to break them down. Modern has taken what some call a low fidelity approach to this, and what we like to call heat in a box. We are getting as much heat into those methane molecules as possible using a patented and proprietary combustion system that we've developed to recycle a portion of the hydrogen we produce to drive our heating. You can see the math breakdown there. We need about 5.5 kilograms of natural gas to make 1 kilogram of delivered hydrogen. That is mostly a byproduct of the masses of carbon and hydrogen within a methane molecule itself. It's about 12 to 4 carbon to hydrogen. We produce about 1.3 kilograms of hydrogen. We recycle about 30% of that back into our combustion system. The byproduct from that combustion is steam. And the other byproduct is that carbon black powder that comes out the other side. Gas, for the most part, in the US and North America, is about 3 to 5 times cheaper than electricity, depending on where you are, which means that you're able to break these methane molecules at 30 to 50, for 33 to 20% of the cost of what you would do if you were running this process off an electric heater or using a plasma torch. We think that this is a huge value added for these industrial operators that are extremely, extremely sensitive to energy costs. Most of the forecasting and decisions they're making about where to place industry, where to place processes are coming downstream of where they can find the cheapest energy. And if you can tell them that they can use their existing gas contracts, their existing gas supplies in a clean way, that's something that they're really excited about. And that's really what we're designing these systems around. We want to make this as fast and easy to adopt for industrial operators as possible. We do not require significant electricity use, which means you don't have to wait for a grid connection in order to start producing hydrogen. We do not rely on hydrogen pipelines. We do not need any rare earth or low volume materials like catalysts in order to make our process work, which means that this is scalable at a fairly rapid rate. And we reduce the reliance on new build. We all want to get to a clean energy future. If it takes the amount of time or even half the amount of time it took us to build out the infrastructure of today, we're going to be waiting a long time, which is why we are of the belief that we should take advantage of that infrastructure wherever we can. Between the US and Canada, there's about 3 million miles of transmission and distribution pipelines in the US that are mostly already paid for, by and large safely operating, delivering huge volumes of gas. Around, ballpark natural gas today is the same energy delivered as solar, nuclear, hydro, and wind put together. It's a massive energy source that is clean and is cheap and domestically produced, and we see it as our job to clean that up to make sure that we don't have to rebuild all of the infrastructure to get us to a clean future. This was an animation that unfortunately is in a PDF, so it's not going to come through, but this is how we see our systems interfacing with existing operations. We are fairly agnostic as to whether we live behind the meter or in front of the meter. All of our customers today are utilities that see this as a way to deliver their customers that are pressuring them for clean fuels, a way that fits with their existing model. You can site these directly on site with industrial operations, with municipal fueling facilities, and all you've got to do is effectively truck the carbon out instead of trucking hydrogen in. Architecture-wise, what we're building is modular and scalable in a way that many chemical plants are not. The chemical plant model is great if you're an EPC. It's not so great if you're anybody else involved with the process. So what we want to do is try to make sure that this is as simple as dropping Lego block-like systems onto your site to allow for scalability. Most of the customers that we talk to are not ready for 100% hydrogen today. They want to get to that point in the future, but they know that they need to retrain their people, they need to update their equipment, their safety processes need work, and if you are going to build a chemical plant to serve that hydrogen demand, you're probably going from 0 to 1, 0 to 100%. What this modular architecture enables is for us to meet the customer where they're at. If you need to start at a 10% blend because your equipment can handle it and your people are ready for it, we'll drop X number of systems that meet that 10% blend, and gradually over time, we'll start bringing more and more as they get more comfortable. It's a model that is a lot more custom fit than designing a one-off chemical plant, and allows us to build these in, by and large, a factory format, which drives the cost down much, much faster. And really the main thing that I would love for you all to take away is that we're creating value from carbon. Carbon is seen by many folks as a liability. We see it as an opportunity. The carbon byproduct that we make, we like to call it a co-product, not a byproduct, is effectively used today in asphalt operations. Our carbon has been deployed now, whoops, I think we're missing a slide there, but our carbon has been deployed in 6 US states and up in Alberta and Canada in asphalt projects that are widely ranging in size and scale. But asphalt producers love our material. For one thing, it is cheaper than what they're paying for today. We offset a portion of the binder that goes into binding the asphalt together. Prices for asphalt binder have tripled over the last 15 years as refineries squeeze more and more gasoline and diesel and jet fuel out of their operations. That leaves less asphalt bitumen behind, which means municipalities pay more per mile of roadway. It means your potholes are coming apart faster because the quality ends up being lower. And it's still extremely emissions intensive. So this is a three-pronged win for a lot of these asphalt producers and municipalities, because not only is our material a better performing material, we see strength increases of about 15% along with extra ductility. We see less rutting, we see less stripping. We also see upwards of 40% emissions reductions. Our material has a pretty incredible ability to lower the required energy to make the asphalt itself, as well as being a cheaper product than what they're paying for today. So instead of venting all of the CO2 into the atmosphere, it would be pretty great if we could turn it into roadways. I've got a minute or two here to take questions, but that's about it. How do you want me to do questions? I can repeat the question back, or do you guys have a mic? Okay. No, that's okay.
Do impurities like sulfur participate out, or do you have to pre-filter those?
I will caveat it with depends how much. With most of the sulfur that we see in gas supplies, it passes through into the carbon. The asphalt producers don't mind it. They tend to say that it helps their process stick together. If we were going to be putting that in other applications, I'd have to talk to you specifically.
Do you have a booth here, or?
What was the question?
Do you guys have a booth?
We do not have a booth. I'm the only, our director of product is somewhere around, but we do not have a booth, no, sorry. Yeah, just come find me. I'll make sure she gets to you. You're way in the back, but.
So as your pyrolysis reaction is going on, the carbon gonna build up within your reactor. So how would you tackle on your catalyst deactivation issue, or you have a way to regenerate your catalyst continuously?
Yeah, so we are fairly unique in the pyrolysis space in that we don't use a catalyst. We are able to, because of the, I probably can't say that, because of the way we've set up our architecture, we don't rely on a catalyst, and we actually see some auto-catalyzation from the carbon that's dissolutioning from the methane itself. You do have to get the carbon out, and that can be a challenge, but that's where most of our IP and that's where most of our engineering work over the last couple years has been, is to make sure that we can operate continuously.
So if I understand correctly, so you hit messing up and without any catalyst in your process, and
correct.
What form of carbon as a product are you producing, if I may know?
Yes, so it is, we call it solid carbon because it doesn't match exactly any of the ASTM standards for carbon black as they are today, but it's very close to like an N990 grade carbon black.
Thank you.
Back corner.
Great presentation. So a lot of folks in the methane pyrolysis space talk about using the sale of the carbon material to basically subsidize the cost of hydrogen.
Yep.
Because you always start out at one hand behind your back because you never can get cheaper than the cost of your methane feedstock.
Yep.
So I'm curious, where do you see your ability on an LCOH basis? Where do you see this at scale, and where can you get to on the cost of hydrogen?
Yeah, so part of that is a business model question in that some of our customers want to own the carbon, and thus they factor it into their total cost ownership model. Some don't care about the carbon, don't want to see it, leave it to us to manage and deal with. Long term, we expect our levelized costs to be somewhere on the order of $1.50 to $2.50 a kilogram, depending on your gas quality or your gas cost locally, your system configuration, what CI target you need to meet. We have some levers we can play with on that front, but that's before you factor in any of the IRA credits and before any of the investment tax credits as well. I think I'm out of time. Thank you guys very much.